Welcome friends. So today we will be discussing numericals on fixed end beam. So find the fixed end moment of the beam shown in figure. Also plot shear force bending moment diagram. And then a beam is given of span 9 meter, 3 plus 6 total 9 meter, and then on left hand side support A, it will develop fixed end moment MFAB and vertical reaction VA, whereas on right hand side it will develop right hand side at support B, it will develop fixed end moment MFBA and vertical reaction VB. So as such we have four unknowns. So using just equilibrium condition we cannot solve them, but we'll use the formula that we have derived to calculate this fixed end moment. Now these problems are very simple if you know what are the standard formulas are and what are their sign convention. So for example, this problem we can convert into, we will first calculate this fixed end moment. Since we already know if there is a concentrated load acting, then what will be the fixed end moment. We also know how to calculate fixed end moment if there is a UDL. So the total fixed end moment, generally fixed end moment are also written as FEM, fixed end moment. So the fixed end moment is equal to fixed end moment due to UDL plus fixed end moment due to point load. So UDL, you can just you apply UDL and calculate fixed end moment, and then apply fixed end point load, calculate fixed end moment. By chance if you have some more load, then you have to go on doing the same procedure, you have to calculate fixed end moment for individual load. So here we have only two loads, point load and UDL. So we will be calculating fixed end moment due to UDL separately and fixed end moment due to point load separately. So this is again typical application of principle of superimposition. So we are calculating two effects separately and then we are adding them. So for this is a standard case for which we already know how to calculate fixed end moment. So then here the moment which will develop, we are calling it MFAB1, and the moment here at support A which is developing, we are calling it MFAB2, whereas on right hand at support B, the fixed end moment due to UDL, we are calling it MFBA1, whereas in the second beam the fixed end moment developed at other end, we are calling it MFBA2. So total fixed end moment at this location at B support will be addition of this two, and fixed end moment at A support will be addition of this two. So MFAB will be equal to MFAB1 plus MFAB2. So we already, the most important part is the sign convention. So this formula, whatever we are writing with this sign convention, we have derived. So for this problem it is simple, but especially you need to be careful when there is a sinking of support, or if there is a concentrated moment is acting. So here the fixed end moment due to UDL will be WL square by 12. The moment that develop at point A due to UDL will be in counterclockwise direction, whereas at support B it will be in clockwise direction. Similarly for the point load moment, point load force, the fixed end moment develop at A or left hand support is it will be in anti-clockwise direction, whereas the moment that develop at other end on right hand end or B end, it is clockwise moment. So this is clockwise, this is clockwise, so we'll add clockwise moment, these two are anti-clockwise, then there will be a addition. So moment due to UDL is equal to WL square by 12 plus moment due to point load will be WAB square by L square. Both are in anti-clockwise direction. So W here it is intensity of UDL, which is 8. L is a total span 9 meter. So L square divided by 12 plus here W is a concentrated load, so W, which is 30, then A, this distance of point load from left support, that is A, which is 3 meter, and B is the distance of point load from right hand support, which is 6 here. So the friction moment equation for point load on left hand end is equal to W A B square by L square. Here you need to remember that this is a square of B portion, not A. For like right hand support, it is A square and then B. So that's only the difference. So then we will substitute this value, and after calculation what we get is like friction moment at point A is equal to 94 kilonewton meter, and that too in anti-clockwise direction. So this is how you can calculate friction moment. The next part is like we'll calculate friction moment at support B. So at support B, again friction moment will be equal to friction moment due to UDL, friction moment due to UDL, friction moment due to UDL, and then friction moment due to point load. So friction moment will be WL square by 12, which is in clockwise direction, and due to point load it is WA square. Now here it is square of A, there it was a square of B, so WA square B by L square. So like you just substitute value of WL, like capital W, then A and then B, and you substitute, you will get, no doubt this is same part, so remaining the value will remain same, only like here instead of 6 square now it is 3 square, so this value get changed 20. So friction moment will be equal to 74 kilonewton meter in clockwise direction. That's how you can calculate the friction moment of a beam. Once you know the friction moment, then easily you can calculate the vertical support reaction. That is using just condition of equilibrium you can calculate. But here there is a slightly change while calculating bending moment diagram. Shear force, it is still same, you calculate support reaction using conditions of equilibrium, because now already we know these two forces, only unknown will be this vertical reaction. But instead of doing that, what we do, we convert this problem into two parts. One with external load, if you remember, we call this as a release beam. So this is release beam with external load, and then release beam with end moment. So we already know how many is the like end moment. Now again, using principle of superimposition, you can say that this beam can be converted into this two part. Now we have to plot shear bending moment diagram for this part, and then bending moment diagram for this part. The bending moment diagram for this, we call it like a mu diagram, and the bending moment diagram for this part is called mu dash diagram. So again, like if you want to calculate reaction, simply like on this whole beam itself you can find out the reaction. But since I told you like we won't be doing in that way, what we'll do, we'll convert this problem into two part. So first beam you analyze, you calculate this vertical reactions. So if you solve this problem, then vertical reaction will be again using condition of equilibrium, you can calculate summation of moment about point B is equal to 0. So we will be taking moment about this point, then it is like 8 due to UDL multiplied by span square by 2. This is typical moment of UDL about some at support, plus then this point load, which is like 6 meter, so 30 into 6, and then like we want to calculate moment above and then moment due to this VA. So VA into 9. So if you multiply this 9, it will come here in denominator. So if you solve this, you will get VA equal to 56 kilonewton in upward direction. Now here also, like VB1 is like this support reaction, which will be equal to addition of vertical force should be 0. From that you can calculate this part. So since you know already how to calculate reaction, I am not doing it in detail, but then I have written it here. Now for this part also we have to calculate this vertical reaction, right? So since there is no load but there are unbalanced moment acting, so like if you add this two moment, there will be some unbalanced moment, right? So initially I am assuming both forces are like upward, though I can understand that like resultant moment of this two is like something in like anti-clockwise direction. So this two together will try to rotate beam in anti-clockwise direction to like bring back to 0 position. The moment should act, like support reaction should act like this. So anyway, like it should come automatically, right? So again you take moment about point B, and then you will get answer like WA2 is equal to 2.22 kilonewton upward, since we get positive answer, and summation Fy equal to 0. If you do, there is no vertical force, so VA2 must be equal to minus VB2, and from that we can say that VB2 should be equal to minus 2.22 kilonewton upward, because we have assumed upward, and VA we already got 2.22. So it so finally since we get minus answer, so final answer would be like 2.22 kilonewton downward, right? Now the total vertical reaction of this beam here, then it will be equal to the addition of this two plus addition of this 2, right? That way you can calculate the total reaction, total vertical reaction. But anyway, we are not interested it immediately. First we'll calculate the bending moment diagram, and then we'll see the remaining part. So now we have to plot bending moment diagram for this part, this simply supported beam or release beam for external load. So this bending moment diagram will look like a typical parabola, right? So again, like you can calculate, we already calculated this vertical reaction, but remember this vertical reaction we have to consider only for this beam. We should not add this part, because this beam is separate, this beam is separate, we are adding them, so that will get the final one. So we are plotting bending moment diagram of this beam, so this part, and the vertical reaction here are 56 kilonewton and 46 kilonewton. So if you plot bending moment diagram, it will be a parabola, since you have UDL all over the span. And then next we have to no doubt the peak portion will it won't be at the center, since we have point load. So to find out the location, what we'll do, we'll take mx equation. Say we'll write mx equation from right to left. So like we are writing from this end, because from this end you have this vertical reaction. So instead of doing that, it is easy to write down from like right end. So it will be 46 into x, 46 into x, and this will cause like positive moment or sagging moment, whereas this UDL will bring this end down. So it will be negative 8.8 into x square by 2. So this is typical moment of UDL. And then for the maximum, we should differentiate this mx and we should equate to 0. So if you do that, then easily you can calculate the distance x is equal to 5.75 meter from A. So from this distance, like from this peak distance is at a 5.75 meter from support A, right? And then simply like you connect this point, so we will calculate this maximum value. So again, in this equation of mx, we have to substitute like x equal to 7.75. If you substitute that, you will get the value of 132.25 kilonewton meter. So this value is 132.25 kilonewton meter. This diagram is called mu diagram. This diagram is called mu diagram. Now we have to take a second part, the beam, release beam with fix and moment. So we already know this reaction. Even without this calculation, we can plot this bending moment diagram. Since we have this moment at right hand support, there is no other load in between. So on right hand side you show this moment, on left hand side you show this moment, and that's all you get. Otherwise, if you want to do the calculation, then like here bending moment, since we have concentrated moment, so we have to calculate bending moment on both the sides. So if you calculate it on like left hand side, then it will be bending moment at point A equal to 0, since there is no moment. But if you cross this point, then you will get this moment, which is like a this moment. Because of this moment, end is coming down, since it is anti-clockwise moment. So that's how it is minus 94 kilonewton meter. Then here we are using like typical sagging and hogging notation. So sagging moments are positive, hogging moments are negative, right? Even here we did the same. So this moment will be bringing end down. This moment is bringing end down, so that's how it is minus. Then there is no any force in between. So at right hand end, if you are on this side, then this moment will be there. If you cross this, then there won't be moment. So if you are on left hand side of point B, then the fix and then we have to consider this fix and moment, so which is minus 74 kilonewton meter. Again, it is bringing this end down. It's like a hugging moment, so minus sign. And if you cross this point, then on further there is no moment or no load, so their moment will be 0. So that's how you should start from 0, 0. Then this is like a 94 kilonewton meter, and this is 74 kilonewton meter. But you remember, you understand, this is negative moment, this is positive moment. Though we are not using one principle here, but just for your information, this mu and mu dash diagram, if you try to calculate total area of this positive and this negative moment, then it should be same. Though we are not using this principle now, but to solve some other problem, we may other way, like we can derive this fix and moment. In that case, we use this principle. First, the area of this positive mu dash diagram and the area of this mu dash diagram, both are equal. Again, if you try to take a moment of this mu dash diagram about say right or about left or right point, it must be equal to the area moment of this area about say like left or right point, right? So using this two principle also we can calculate fix and moment. But anyway, that is different. We have already calculated the fix and moment using consistent deformation method. So this is like you get two bending moment diagram. Now what we will be do, we'll superimpose this part on this like positive bending moment diagram, or this mu dash diagram will superimpose on this mu diagram to get the final answer. So final answer, if you want to calculate like for this beam, then this is like we have just flipped this this moment and we have overlapped it on this diagram, so then it will look like this. So here you will get minus 94 kilonewton meter. Here it is 74 kilonewton meter. I have shown all the figure. Now here you see this total vertical reaction is equal to VA is equal to VA1 plus VA2. So VA1 and VA2 both are upward, so there will be addition. But at VB, one is positive, another one is negative. So like 46 minus 2.22. So there will be subtraction and you will get this as a like final vertical reaction. So that's how you can calculate final vertical reactions. Now we have to also like when you superimpose, then we know the maximum negative bending. So this is like negative bending moment will be here and here. So when you superimpose, this portion will get cancelled out, and this is the only bending moment diagram that remains. So this is the only bending moment diagram. Now this maximum bending moment at right hand side, we already know that it is 74. On left hand side it is 94, but in between we need to calculate what will be the maximum. No doubt for this parabolic portion we already know where the maximum was. It was some 5.75 meter from this end, but now we need to calculate where it will be. So that either you can calculate from the shear force diagram, or you may again write down equation of mx considering this moment, and then like differentiate it, then from that also we can calculate. I have calculated it from shear force diagram. So then I calculated location of point of contra shear, and we already know that at point of contra shear you get the maximum bending moment. So then shear force diagram I have plotted. So since we know all this like reaction, we have to start from this end. Since in shear force diagram we do not consider the moment, so this moment won't come, only vertical forces will come. So here it is like upward. So when we calculate shear force from left to right, upward we assume positive and downward we assume negative, whereas like if we calculate from right to left, upward is negative, downward is positive, right? This is the sign convention that we use. So we'll be using this sign convention, and this like a final beam or with this reaction we'll calculate. So if you do that, then shear force at like B point on shear force at A point, this is it, not B. Shear force at A point on left hand side, there won't be a force because we are on left hand side of this A point, so it will be 0. But if you cross it, then on right hand side of A point you will get this reaction, because if you are coming from left to right and you are already on like right hand side, so you have to consider this vertical reaction. So this reaction shear force calculations are typical, which we already done so many times in a class, so I'm not going to discuss it in more detail. But then shear force at A point is 58.22 kilonewton. Then shear force at C point, again there is a concentrated point load, so we have to calculate on both sides. So if you are on left hand side of this point, then we won't be considering this, there will be UDL and this vertical reaction only. So then it will be equal to 58.22 minus 8 multiplied by 3. So then this UDL is downward and we are calculating left to right, so it will be negative. And then if you substitute value, you will get 34.22 kilonewton. Then on like right hand side of C point, now if you cross this, we have to consider this one. So then in addition to this, there will be like a downward 30 kilonewton. So again downward minus, so downward minus, so minus 30 kilonewton, and then final answer will be 4.22 kilonewton. Then bending moment at like B left point, B left hand side, so you can calculate it from right to left, and upward force we write negative. So then it will be like vertical reaction 43.78 kilonewton. And then on like right hand side, if you are on this side, there is no force further on right, so the bending moment will be 0. So you just connect these all point and you will get this bending moment diagram. Now we have to calculate the location of point of contra shear. So again use this similarity of the triangle. So similarity of triangle, we have to consider this one triangle and this another triangle. Since these angles are like same, so this two triangle must be a similar triangle. So using the principle or the property of similar triangle, you can calculate x distance. So the x distance is 5.47. so from this value you should understand the peak bending moment diagram for parabola. It was like at a distance, it was at a distance 5.75 meter, but for this combined effect it is at 5.47 meter. So it has shifted towards the B point, right? So again there we have to calculate maximum bending moment. So like you substitute x equal to general equation, like you calculate here bending moment considering this fixed moment. So if you write down that equation, you will get the value as 45.8 kilonewton meter. So this maximum value here, it will be 45.8 kilonewton, and it is at a distance 5.47 meter. That is what we have got here. We should also calculate this point of contra shear, where the point of contra shear will be. So we'll do that calculation. So for that, again what we have to do, we have to write down mx equation. So if we want to calculate right hand side point of contra shear, so what I'll do, I'll write down the equation, mx equation, and equate it to 0. So mx equation will be first this fixed moment, this vertical force multiplied by x distance. Since we want to calculate the location, so we are writing in terms of x, equal to 74, that is this fixed moment, which will be negative. Then due to UDL, it will be 8 multiplied by x square by 2. So this is like a quadratic equation. Now at point of contraflexure, mx should be 0, so we are substituting 0, and then we are solving this quadratic equation. You will get two values, one is 8.85 and 2.09 meter, but 8.85 is like invalid answer. It will be invalid answer, since the maximum bending moment, positive bending moment, is acting at 5.47 meter itself. So x cannot be more than this value, because here we are getting positive value, so it should be less than this, and like here we are getting positive value at a distance 5.47 meter, whereas from negative to positive it is changing. So there must be a point of contraflexure between this 2 point itself, 0 and like distance 5.47 meter, since we are calculating it from right end. So correct answer would be 2.09 meter. So hence x equal to 2.09 meter from the support B. So the location of point of contraflexure on right hand side, this right hand side, it will be x equal to 2.09 meter. Now similarly we can calculate it for this point of contraflexure as well. Now we will writing the mx equation for left hand side point of contraflexure. So again mx is equal to 58 into x distance. So we are calculating at x, we are assuming it will be on like left hand side of point load. So that's how I'll consider this point load. Then since it like from here itself you can understand it should be on left hand side. So when you draw this bending moment diagram, approximately it should be proportional, then only you will get idea whether you should consider this point load or not. Then first, due to this vertical reaction which is equal to 58.22 into x, minus 94, this fixed end moment, minus due to UDL 8 into x square by 2. And so again this mx should be 0 since we are calculating point of contraflexure. So like we are like rewriting this equation, and then this is again a quadratic equation. You solve this quadratic equation and you will get two values. One is 12.7, another one is 1.84. Definitely this 2.7 is more than 3.53. 3.53 is what? Like this distance. This distance is 3.53, and at like from support A at a distance 3.53 meter we get maximum positive bending moment. So the point cannot be beyond that, right? So it should be since we are changing from negative to positive, and maximum positive we are getting at 3.53 meter, then this point of 0 should be in between. So then correct answer would be 1.84 meter. So x will be 1.84 meter. That's how like you can solve the problem. So just to revise this, like what we did, we have this problem. So we converted this problem into two parts. First to calculate fixed end moment. So broadly if you see, there are two things that we do. One, we calculate fixed end moment, and second we do like bending moment calculation or mu and mu dash diagram. So calculating fixed end moment is like easy. You just use a standard formula and you will get the answer. So you have to consider the effect of each load separately, and then you have to add them to get the final fixed end moment. And in case of for calculating bending moment diagram, what we have to do, we have to convert this problem into two beam or two release beam. Again, using principle of superimposition we can do that. So you convert this into two beam, one with simple support and external load, and second part like fixed end moment without any external load. So the bending moment of this diagram we call it mu diagram, and the bending moment diagram of this part we call mu dash diagram. So we have to superimpose this two to get the final like bending moment diagram. No doubt this is how we will get. And then we have to show the location of maximum bending moment, point of contraflexure. And plotting shear force diagram is easy. It is typically the same. The way we used to solve that is same. The difference is here is also the total vertical reaction will be equal to the vertical reaction of this beam plus vertical reaction of this portion, and vertical reaction of this part, and this part will be the total. So that's how like we can solve the problem. Finally we have calculated point of contraflexure. So this part you already know how to calculate point of contraflexure, point of contra shear, so I'm not going to discuss that in detail, or you should do the practice. Now we'll discuss the second numerical problem. So in this problem like find the fixed end moment at the support and draw the bending moment diagram. So here only bending moment diagram is asked. For the fixed end beam shown in figure, if B sinks by 10 mm, take E equal to 200 kilonewton per mm square and I equal to 2.75 into 10 raised to 7 mm raised to 4. So this is given. Now again if you see, like we have this concentrated load, moment and sinking of support, three parts. So we should calculate the fixed end moment for these three parts only. And to calculate this bending moment diagram, we'll be converting this problem into this two part, right? So first we'll calculate the fixed end moment. So fixed end moment, like fixed end moment is equal to fixed end moment due to point load plus fixed end moment due to moment and plus fixed end moment due to sinking or settlement of the support. So because of point load, because of moment. So here the sign conventions are important. Here if you make a mistake in sign convention, then your answer won't correct. And again, with this sign convention, there like formula should also you should remember. If you make a mistake in that, then again it will be a problem, because some books may write this problem like with this sign convention also. So they changes little bit of formula, plus minus sign they change in formula, but we will be following this one, right? Even like same for the settlement of the support. If your right hand settles, then the moment develop will be at both end, it will be in anti-clockwise direction, whereas if it is left hand, then at both end it will be in opposite direction. This is anti-clockwise, this is anti-clockwise, here it is clockwise, clockwise, and this is clockwise and anti-clockwise, right? So this is like important part in this problem. Remaining thing is again same. So fixed end moment at A will be equal to W A square A B square by L square. So W A B square by L square. This moment will be this moment, which is anti-clockwise. So anti-clockwise. Then minus the fixed end moment. This is what I was telling. So fixed end moment due to concentrated moment can be written in this way also, but in that case this will be, instead of 2a minus b, they will write b minus 2a. Even some people write it in terms of L also. So like here with this sign it is 2a minus b, right? So m into b in bracket 2a minus b by L square, and this moment is clockwise moment. This moment is clockwise moment, right? And then since we are assuming like anti-clockwise positive, so this will be minus, this will be again plus. So plus 6 EI delta by L square. This moment will be anti-clockwise, right? So anti-clockwise, anti-clockwise we are adding, and clockwise we are subtracting here. So that hardly matters, like even if you consider it negative, negative, and this positive, then also okay, you will get the same answer. So like if you substitute that value, you just substitute the value of A, B, M, corresponding values you substitute, and then again here you need to convert E and I in terms of kilonewton meter, since the given values are in kilonewton mm square. Here it's in mm to 4. So if you convert that into like you have to convert that into kilonewton meter, since all other values are in kilonewton and meter. So this 2.75 into 10 raised to 4 and this 10 raised to 9, that is like adjustment I have done. So I hope you know that. So once you do that, like you will get the answer. The values will be 2.64.6 meter. This value will be minus 51.2, and the settlement it will create only 3.33 kilonewton meter. So you add them and you will get the final answer, that fixed end moment at point A is equal to 216.7 kilonewton meter. This will be in anti-clockwise direction, since we have assumed anti-clockwise direction positive here, right? So this much is the answer. Now at point B, definitely we should consider clockwise positive, so your answer will be positive. So this is fixed end moment due to point load, this point load, so this is in clockwise direction. Here also this is in clockwise direction. For this problem you remember, though if moment is acting clockwise, this support moment will also be clockwise. If it is anti-clockwise, then this support moment will also be anti-clockwise, and formula will remain as it is. There is only change, right? Only this direction get changed if it is clockwise. But since here the moment is clockwise, so this fixed end moment will also be clockwise moment. So fixed end moment is clockwise. So clockwise positive. This moment which will develop here at support B due to settlement, it will be anti-clockwise and it will be negative. So again I am telling, either you can consider this minus, this plus, then final answer won't change. So either way you can do. So this moment is again you substitute value. The point load is 180 kilonewton. A distance, yes, again like A distance here it is like a 3 meter, and from this end it is like 3 plus 7. Sorry, 3 plus 4, 7 meter. See, like in case of concentrated moment also we need to write down AB value, and for point load also we need to write down AB value. But for point load, like A value will be 3 meter and B value will be 7 meter. But for concentrated moment, A value will be 6 meter and B value will be 4 meter. Right? So that is what, like I have substituted the value here. If you see, A is 3, B is 7, and for moment A value is like 6, B value is 4, right? That's what you have to substitute value. Here there is no AB value, so like only L value we need and delta we need. So you substitute this value and you will get the answer 129.3 kilonewton meter. That's how you can calculate fixed end moment. Now we'll calculate the bending moment diagram. So again, for calculating bending moment diagram, I already told you we'll be considering this two beam, like this given beam we can convert into two release beam. We'll apply the external load. We'll calculate the bending moment diagram for this one, which we call mu diagram, and then for fixed end moment again we'll plot a bending moment diagram, and that will be the mu dash diagram. So finally we will overlap them. So like this is simple supported beam with a point load and concentrated moment. So like typically you calculate this reaction, we call it like VA1 VB1. So you use condition of equilibrium since we have already two unknowns. So VA1 plus VA1 plus VB1 is equal to 180 kilonewton total downward, and then taking moment about point A. So if you take that, you will get VB1 equal to 70 kilonewton. So again you substitute this value here, you will get VA equal to 110 kilonewton upward. Now calculating BM calculation. So this is mu diagram, right? So this is BM calculation for mu diagram. So this is the sign convention that we use. So again, like typically bending moment at point A on there is no concentrated moment, so and there is no further load on left hand side. So bending moment at point A should be 0. At C, like C, it will be this force into distance, which is 3 meter. So 110 multiplied by 3, you will get moment of 330 kilonewton meter. Then at point D we have concentrated moment, so we have to calculate left right. So we will calculate first left. So again here we are calculating on left hand side, so we won't be considering this moment first. So it will be moment due to these two forces, which is equal to 110 multiplied by 6 distance, 180 multiplied by 3 meter. So 110 multiplied by 6 minus 180 into 3. So you substitute and you will get 120 kilonewton. Now this moment is like if you see, like when you calculate moment on right hand side, we are considering this sagging moment positive. So because of this moment, if you see this, like left end is going up. If you rotate this beam, then this end is going up. So if you are calculating movement from left to right, then we have to consider this as a positive moment. So it will be a positive moment, and the value is 160, so we'll add it to here and you'll get 280 kilonewton meter moment, right? So like here it is 120 plus this 160 and you'll get the answer. Now for mu dash diagram, this we'll consider this fixed sign, and if you remember, like last time we got negative positive, that's how I have written it directly with proper sign. This will be VA2, this will be VB2, right? So then we'll calculate VB2 and VA2. As such we don't need this because we are not plotting shear force diagram, but if you want to plot shear force diagram, then definitely we need to calculate VB2 and VA2 because we need the final reaction for plotting shear force diagram. But since in bending moment diagram we are interested only in mu dash diagram, which you can directly plot without considering this fixed vertical reactions. So now again, this is typical bending moment calculation for this mu dash diagram. So this is mu dash diagram. So mu dash diagram. Now we need this value at any distance x. What will be the bending moment? For that again you can convert this two triangle. One is this triangle and another one is this triangle. You use property of similarity and you can write down mx equation there. So mx equation will be this moment, this much moment plus this height. So this height we can calculate using the similarity of triangle or say interpolation, and that comes out to be 129.3 plus 8.74x. So at any x distance from B support, moment we can calculate, and we need to calculate at two locations. One is this one, another one is this one. So we'll calculate that moment. So moment at 4 meter, moment at 4 meter here we need to calculate because we want to check whether the line will pass below this point, above this point, where it will be. So to know that, if you calculate, it is 164.29 kilonewton meter, and at 7 it is 190.48 kilonewton meter, right? So like here at a distance of 7 meter from B point, which is like C point, at C point we are calculating this moment. Now since this 164.28 is less than, it is less than this 280 kilonewton and more than 120 kilonewton, so it will pass somewhere in between, right? So when we superimpose this diagram, like here you can understand, like when you superimpose this diagram, then this point is in between, right? This value here, this value will be 164.28. so this height, if you calculate from this point to this point, then it is 164.26 kilonewton. Similarly, like this height here, it is 190.48 kilonewton. So this height is 190. So when you superimpose, we should also calculate resultant bending moment diagram. So this part will get cancelled, only this like hatch portion will be there. So like in between there is a negative moment. So here, since the moment developing minus negative moment developing is 164, so 164 minus 120, so this will be like 44.26, and this value we can calculate by subtracting 164 from this 280 value. So if you subtract that, we will get a value of 115.74 kilonewton. Similarly, this height we can calculate, because if you remember, this mu dash diagram is positive and mu diagram is positive and mu dash diagram is negative. So this negative will cancel out positive effect, and then finally this much will be the remaining bending moment value. So this bending moment value is equal to, this height is 330 minus this 190.48, so the remaining value is 139.52 kilonewton. So that's how you can solve the problem. You can plot the bending moment diagram. So we'll stop today. So this is the end of this part. In next class we'll start a new topic called Clapeyron's three moment theorem, and it is typically useful for continuous beam. So in next class we'll discuss that three moment theorem.